mean the final project.
What is the
Yeah, I mean the final research project submission due date.
final research project?
Yeah.
It's like a research paper though.
Yeah, I mean the one is gonna be the overdue
It's
today.
due? No, it's not. It's due by next week,
Oh,
Wednesday, right? May 13th.
that day. But yeah, on the price rate it's showing out like overdue 30 minutes ago. That's why I just like figure it out. So
Oh no, that's about uh, the one is due is about a one-page summary.
oh,
You need to submit a one-page summary with the data set, right? And then you're gonna submit this by next. It's due. Okay, I have to change it, right? It's
okay, yeah.
no, it's not actually. I'm gonna change it a little bit, right? Don't worry. I
Okay.
see what you mean. Yeah, it's not
Yeah.
due. It's not due by the end of today. It's due by next week.
All right.
You haven't. Yeah. So let me just update it. So this question is about the binomial probability distribution. Binomial probability. We got to check all four conditions. First one is all trials are independent. So here we have 10 new messages. So all trials are independent. The simple random sample. So pick a simple random sample. Then all these trials are independent. That means that. Secondly, so we have outcomes in two categories. Either spam email or non-spam. And spam is what we consider a success event. And then non-spam would be the failure event. Spam or non-spam. And thirdly, probability success remain constant. Probability success in this case, probability success probability of spam email is remain constant. E is equal to 47%. And then Q is 53%. 53% of emails are non-spam. So Q is 53%. And then last one. Fixed number trials, right? Fixed number of trials. In this case, only 10 trials, so it's definitely fixed number. So, yeah. And once we have checked, so indeed it's a binomial distribution. Then we can do the calculation. So for A, we are looking for exactly six of them are spam email. So part A, A equals 10. For B, success 0.47. Q is 0.53. And X here is six successes. So the formula is P of X equal to n factorial over x factorial times n minus x factorial and P to the X times Q n minus X. So we're picking 6 successes out of 10 trials, and that's why it's a combination. So 10 factorial over 6 factorial times n minus 6 factorial times 0.47 to the 6 times 0.53 to the 4th. 10 minus 6 is. And so that's how we get the result. And I'll go back to let me show you the result in Excel. So it's going to be n factorial, 10 factorial open parentheses, 10 factorial divided by 6 open parentheses, 6 factorial times 4 factorial. That will be the numerator, and then multiply by 0.47 to 6 power times 0.53 to the 4th power, and then we get the result. With the formula minus I. Let me see. Oh yeah, it's not. It should be another formula. FACT factorial. And it should be FACT 6. Times FACT 4. That should do it. Yeah, so we get 0.1786. And if you want to double check, we can do this binomial distribution. The number of success will be 6, trials 10. Probability success 0.47. We're not accumulating. We are looking for the probability density function at that given moment. That's 6. Yeah, trial probability success. Oh yeah, force. It should be force. No, it's not a probability. We're not accumulating. So it's a 0.1786 here. So the answer to the first part is 0.1786. So that's part A. Part B, we are looking at the same context, at least 6. So we need to do P of X equal to 6, 7, 8, 9, and 10. So we're going to do calculation like combine all of this. So we do P of X equals 6. We already have that. Plus P of x equals 7, 7 successes, plus P of x equal to 8, plus P of x equal to 9, plus P of x equal to 10. We did the 6 already, which is this. And then we're going to get 7, 8, 9, and 10. And again, we apply the same formula and also look it up, in the formula sheet under the chapter 5 formulas. We are using this formula, binomial distribution. Yeah, I'm going to quickly show you there's a quick way of doing this. It's going to be this. So x, P of x. X here was going to be 6, 7, 8, 9, 10. I'm just going to format this. And let's do the calculation here. The binomial distribution success, we're going to use this number here. For trials, there's the same. Probability success is always the same. We're not accumulating. The last argument is always false, so get a result. Then extend the formulas to the remaining of the calculations, sum up those results, you get 0.3057, right? If you wanted to put decimal place, so the total probability would be 0.3057. So about 30.50% of the chance. So any question about this? And let's look at question 3. We're gonna find a central limit theorem here. Okay, I'll let you try first before we go over the solution. Let's go to the solution. So here, because of sample size is a 50, although it's not specifically mentioned, it's normally distributed for the population, but since sample size is larger than 30, and then all this sample is a simple random sample because it says it's independent. So sample is a simple random sample. That means central limit theorem applies. And here we know population mean is 6. And then population standard deviation sigma is 2.5. And the sample size 50. Basically, we are comparing the sample mean with the population mean. And then here we are looking for the sample average sample mean, which is greater than 6.5 minutes. So first of all, let's draw the bell curve. High. For the population mean in the center, 6. And we're looking for the sample mean. We are comparing the sample mean with respect to population mean and trying to figure out area to the right hand side. So we do the conversion, right? So using the central limit theorem, one formula to represent the central limit theorem is z-score equal to sample mean minus population mean over population standard deviation by square root of sample size. And then we will convert the sample mean to the z-score. Sample mean 6.5 minus 6 over 2.5 by square root of 50. And then we find the z-score. Again, we use Excel. So 6.5 minus 6. You can also try in your calculator. You're allowed to use calculator in the final T. And then we get z-score, which is 1.41. 2 decimal place. 1.41. Now we go back to approximately 1.41. Now we're going to use a table A2 on the formula sheet. So here we're getting this standard normal curve, right? So on the standard normal curve, z-score in the center is 0. Now our z-score here is 1.41. Now we are looking for the area to the right hand side. And we take 1.41, go back to table A2. It's embedded in our formula sheet. So we're going to scroll down and go back to second page. I'm going to see 1.41 here, which is 0.9207. Now that means area to the left is 0.9207, but we want area to the right. So the area to the left is 0.927. Area here on the right here will be 1 minus 0.9207. So this is going to be 0.0793. That's a probability for I. So I'm gonna back to this and get another screenshot for the second part. So for the second part, Bobby, one more time, very similarly, we are looking for the keyword here is between 5.5 and 6.5. So I'm looking for the area in between. Again, put a population mean in the center, 6. This is 5.5. 6.5. And we want area in between. Now again, we got to do a couple conversions. Start with the bigger sample mean. So first one with the bigger sample mean, 6.5. By the central limit theorem, so z-score equal to sample mean minus population mean by sigma population standard deviation over square root of sample size. Here it's going to be 6.5. We did a calculation earlier. It's 1.41. And 2.5 over square root of 15. And this is approximately 1.41. And then for the smallest sample mean, second part, with the smaller sample mean, 5.5. So the z-score is going to be sample mean minus population mean over population standard deviation by square root of sample size. So this is 5.5 minus 6 over 2.5 by radical 50. And this is minus 1.41. These two z-score will be opposite. We can quickly check using the calculator. It's minus 1.41. And we want area in between. So, yeah, so this becomes a standard normal curve. And based on the bigger z-score, we get 0.927. And we want area in between. So you're going to use a bigger area minus smaller area based on minus 1.41. So we go to first page, minus 1.41. And that turned out to be 0.0793. Okay, 0.0793. 0.0793. And the difference is the area in between. So this is 4, 1, 11 minus 7 is 4, and 8. So this is 0.8414. So 84.14%. That's the probability value we're looking for the sample mean greater than 5.5, less than 6.5. Probability is 0.84. Any question about this? So that's question 3, question 4. Hey guys, I'm sending out email to the rest of the class, right? They went to the class. They are waiting in front of the Larry 309 right now. I'm trying to get into contact with them and then tell them to join the Zoom meeting for today's class.
Yeah,
So
Professor.
yeah.
So for me like I cannot like use my Outlook, so I didn't get like
Oh,
from you. So if you don't mind, can you do like pass in the email like
That's
yeah.
what I'm doing right now. Yeah.
Okay,
I'm
thank you.
sending out email to everybody right now
All right.
yeah, I'm just going to CUNY first right now and then you guys can work on that. I don't want to wait outside, But like I get an email from one of the classmates, Oscar, and he told me he's still waiting there. He thought that we're not having class today. Yeah. So I'm doing that right now. Hey Farah, did anyone waiting outside of the class? Hey Oscar, is there anybody else waiting outside of the classroom right now?
Sorry, hello?
Yeah, yeah, Oscar. Did you see anybody else waiting outside of the M309 right now?
Yes, I did.
Can you tell them to join the Zoom meeting?
All right, I will. Thank you. I will.
Yeah, yeah, yeah. Please, thanks. Yeah. So again, the BMC did a email transfer right to the Outlook. So that caused some problem, I guess. I sent out two emails. I sent out an email last night around like 8 p.m. about today's class. So I hurt my back on Monday, and then I couldn't I couldn't come in today. It hurts pretty badly. So right, but the doctor told me it's better to stay home for another couple of days fully recover from the injury. So that's why I couldn't come in. Otherwise, I'll try. Yeah. And then again, because of the email migration, so maybe some of you guys didn't receive my email, but it's okay, right? I record this Zoom meeting section. So I will produce the video and then I will send it to you guys after class, after I finish producing the video. So you won't miss anything, right? Everything will be there. Yeah. Again, that just I know they shouldn't do the email migration in the middle of semester and then mess up a lot of things. But it's okay, right? It's recorded, so we're good to go. Yeah. So now let's take a look at this question here. So this one we are doing the confidence interval in this case. So we're doing the 95% confidence interval. So in this context, we have 200 charges, 18 of them found to be defective. So, and we're concerned about the true population proportion of the defective charges. So in this case, success event will be considered as defective items. So the P here will be equal to X over A, which is 18 over 200. This is 0.01. That's 9%. 9% of items are defective. The Q is good items, so it's going to be 1 minus P. This is 1 minus 0.09, so it's 0.91. Yeah, that's and then sample size 200. And from there, we will find the margin error. So margin error equal to that. And also we need critical values. So 95% confidence. The critical z-score, C alpha over 2, is going to be 1.96. Now you can look it up in the formula sheet. If you go down to the second page, on the bottom right-hand corner, there are 3 critical values. That's 95% is 1.96. 90% is 1.645. 99% is 2.575. Now we are using the 95%, 1.96. So the margin error, it's the maximum likely difference between the sample proportion, which is the percentage of the defective items in a sample, and then percentage of defective items in the entire population. We do C alpha over 2 times square root of PQ over sample size, P hat, Q hat. And go back to the, I just want to show you where to find the formulas. In chapter 7, right here, we are using this formula for estimating population proportion. We are using this margin error formula. You had over sample size. So it's going to be 1.96 times radical 0.09 times 0.91 over 200. And that will give us the margin error. One more time, I'm going to get it done in Excel. So equal 1.96 times square root of 0.09 times 0.91 over 200. And then key enter, we'll get the result, which is going to be this 0.03 0.97, right? 0.0397 is 0.0397. Now from there, we construct a 95% confidence interval using the p hat, which is sample proportion minus margin error. That's lower limit p hat plus margin error. So it's going to be p hat is this 0.09. This one. So it's 0.09 minus 0.0397. That's lower limit. Upper limit is 0.09 plus 0.0397. So the lower limit it's going to be 0.0503. So this is between 5.303 to 0.1297. 0.1297. So it's between those two percentage. And so if you want to put in a percentage portion, population proportion is between 5.03% and 12.97%. So that's basically the 95% confidence interval. Any question about this? Again, if you just joined, right? I did send out email last night, also this morning, about today's Zoom meeting, right? Via the Brightspace. I guess due to the email transfer to the I think it's login to CUNY. They just switched the email to login.cuny.edu. So maybe some of you guys didn't get an email, but it's okay, right? I recorded this Zoom meeting section, and I will produce the video, and I will send it to you after I finish producing this after class. So you won't miss anything. All right, so let's look at question 5. All right, let's take a look at this one. This is about population mean. Right? So estimating the population mean. Again, I'll give you some time, take a look at it, and I'll go over the solution. So let's go over solution. And here we have sample size 50 and 50, and then sample mean. It's 52 minutes. Sample standard deviation S is 8 minutes. Now we are creating the 95% confidence interval. So here, because of the sigma is unknown, so we are doing the t-test. We're using t-distribution. And for t-distribution, we need a couple things. Alpha, it's 1 minus confidence level. So that's going to be 5%, 0.05. And then degree of freedom, it's sample size minus 1. So which is 50 minus 149. Based on those two, we find a critical z-score of the two. So again, we can go back to table A3 for the t-distribution. So go down to table A3. And degree of freedom, we don't have exact match here, but there's a close one, which is 50. 49 is close to 50. So we can use for 50. In this case, 50 and then area in two tails. Area in two tail turned out to be 0.05. And we're going to have an intercept here is 2.009. 2.009, that's the number we're looking for right here. Area in two tails and degree of freedom 50. Yeah. Because there's no exactly 49 there. Okay, so it's 2.009. If you want exact, you can get it down in Excel. So we do t dot inverse probability, that's area to the left. It's so we split alpha in two tails. You get 1 minus 0.05 by 2. Degree of freedom 49. And you get this, right? That's almost the same, right? 2.009. So that's what we're gonna use, right? 2.009. 2.009. And from there, we can find out the margin error. Margin error equal to critical t-score times sample standard deviation over square root sample size. You can also look it up in the formula sheet. It's right here. That's the second one, sigma unknown. We're using critical t-score, t-distribution. And our margin error is this. And then after we find the margin error, we using sample mean minus margin error to get a lower limit, sample mean, adding margin error, upper limit. And so that's it. So it's 2.009 times sample standard deviation 8 over square root of 50. And we get a margin error. So we do 2.009. Times 8 over square root of 50. And that will give us the margin error, and then we're just gonna keep it 3 decimal place, 2.273. So if we run it to 3 decimal, 2.273. Margin error is 2.273 minutes. Now we create the 95% confidence interval. So you do sample mean minus margin error, and then sample mean plus margin error. Sample mean, it's 52. So you do 52 minus 2.273 minutes. And 52 plus 2.273. So the lower limit is going to be 49.727. Upper limit is going to be 54.273 minutes. And so that's basically what this means is with a 95% confidence that the true population mean delivery time is going to be between 49.727 minutes and 54.273 minutes. That's how we create a 95% confidence interval. Any question about this? Okay, let's go back to question 6.
Professor, I have a question.
Yeah, sure. Oscar.
How do you create a 99 point, greater than 99% confidence interval?
99%?
Or more,
sure,
yeah.
Oh, yeah, sure. So if let's say using the same context, but it's 99%, right?
Mhm.
The only difference will be critical T-score will be different.
Yeah.
99% confidence. And degree of freedom is still the same.
Yes, I have a question. What about 6 standard deviations, or I don't know, like the highest possible that you can get without it being 100?
Oh, that's going to be very small though.
I see.
Alpha will be very, very small. 6 standard will be probably 0.000000001.
Okay.
So that kind of and the alpha here will be 1%, which is 0.01. And again, you use these two values, go back to table A3, and you just scroll down to table A3. And again, there's no exact match here, so we're going to use for 50 instead. And 50, and also here, area and detail is 0.01, so the critical T-score is 2.678.
That makes sense. Thank you.
Yep, sure, no problem. So that's the only difference, right? Only difference in this, in the calculation. But yeah, so let's look at the next question here. Yeah, question 6. Yeah, so we're doing a hypothesis test, right? 6 is about hypothesis test. So again, I'll let you try it for like 5 minutes, and I'll show the solution.
Sorry, Professor, I have a question.
Yeah, yeah, sure, Oscar.
What chapter would this relate to?
This is about hypothesis test. So
Okay.
it's on a review from chapter 8.
Thank you.
Different color. So for typical hypothesis testing, step one, we need to figure out which null hypothesis and alternative hypothesis. And then it's key, it based on the claim or like the test we try to perform. So the hypothesis here is a test at 0.0 alpha equals 0.01, whether the average the mean fill, like amount of time it takes to fill the jar differs from 50 milliliter, right? Not so the basically different means not equal to. And then since there's no equal sign, this has to be an alternate hypothesis. So here the mean is not equal to 50 milliliter. So the null hypothesis will be the complement. Initially must be 15 milliliter. And second step, it's calculate the test statistics. Calculate test statistics. And in this case, we are using the central limit theorem. So on average, right, then that's random sample 16, so n equals 16, and then the sample mean 52 milliliter, sample standard deviation is 4.5, so S is 4.5. So since sigma is unknown, so we are using the t-test. Okay, so sigma unknown. So we're doing the t-distribution, t-test. So the formula we are using, just want to point out the formula to you first. We'll go back to chapter 8. And then we are using this formula here. Mean one population, sigma unknown, right? This particular formula. So then we're looking for the t-score. So the t-score here equal to sample mean minus population mean over sample standard deviation by square root of sample size. And the sample mean here, population mean is 50. So it's 52 minus 50 over sample standard deviation is 4.5 over square root of sample size is 16, right here. Sample size 16. And we can get the t-score here. (5.2) minus 5 over 4.5 over square root of 16. So parentheses is 4.5 over square root of 16 is 4. We get a t-score here, so it's 0.178. If you run it to 3 decimal place, 0.178. We get approximately 0.178. With the 3 decimal place. The next thing is using the.
Wait, Professor,
Yeah, sure, yeah.
is that 5.2 or 52?
It's a 52. Yeah, that's the sample mean, 52.
I see, but never mind. Sorry, I was just confused on something.
Okay, all right. Yeah. Any other questions? Open problem. I don't think it looks like something's off. Let me double check. So 4, that's, oh yeah, it's good. It's good. Yeah. No, actually, I made a mistake. It's 52 minus 50, right? So it's 1.778. I overlooked 1.778. So this is off. 1.778. It's 2, right? Actually, we can do it ourselves. It's not that bad. 4.5 by 4. That's 1.1125. 2 over 4.5 by 4. Yeah, 4.125 exactly. So that's 1.178. So that's going to be the t-score. And here we are doing the two-tailed test, right? So alternating hypothesis tells us it's two-tailed test. The third step is using the, in this case, we're going to using the critical value method. The critical value based on two things, alpha, which is 0.01, and then degree of freedom. The degree of freedom is 16 minus 1, 15. So based on those two, we get a critical t-score. So basically, we draw the bell curve. Now we're going to put a critical t-score on the curve. Because two-tail, right? So rejection region are located on both tails. One on the left is negative T alpha over 2. On the right is T alpha over 2. So we get both values on the table A3. Let's go back to table A3. Degree of freedom 15. And an area in two-tail, it's 0.01. So, yes, it is. Yeah, it's 0.01. Yeah. So that will give us a critical t-score here. 15, and then area in two-tail is area in two-tail 0.01, 2.947. So you get a 1 on the right tail, 2.947. And then the 1 on the left is minus 2.947. And I hear that both tails are what we call the rejection region. You see the t-score, when the t-score beyond this 2.947 standard deviation, or like below minus 2.947 standard deviation, we consider those are the extreme values, and then we reject HO. So this is rejection region. The one on the right tail is same thing, rejection region. And then the middle one is called a non-rejection region. And looks like this tested this t-score falling in the non-rejection region. It's between those two values. So then the last part is reaching the conclusion, right? Conclusion. Since test statistics fall in the non-rejection region, so we failed to reject HO. Fail to reject HO. That means this is true, right? So there's sufficient evidence to warrant a rejection that the mean field differs from 50 milliliters at 0.01 significance level. So that's so you can just write the final conclusion as sufficient evidence to warrant rejection of the claim that the mean field differ from 50 millimeter. Of claim and of the claim. The mean field differs from 50 millimeter. The mean field. So that's basically a four-step procedure to perform a hypothesis test. Any question about this?
Excuse me, Professor, what's the word behind the rejection of the C, the claim? What's
Oh
that
yeah,
word?
the claim
Uh,
of the claim that the mean field differ from 50 milliliter. Or maybe let me rewrite it. No worries, right? I'm gonna rewrite this. Let me just rewrite the conclusion here. Just gotta. So the conclusion is that is a sufficient evidence to warrant this is a technical, it's kind of like they have standard wordings for the rejection claim that mean field differs from 50 millimeter. So let's go back. Let's look at next question. It's also about a hypothesis test. That's just different direction. Yeah, again, we give a shot first, and I'll show you the solution in a bit. Let's look at the solution here. So we are testing this claim right here. Investigator believe the company has been biased against the women. And so basically supposedly there should be 46% of female and 54% male. So here the step 1, HO and H1. So bias against women usually is a bad thing, right? So that means P will be less than 46%. So they hire less women. That's biased. And then the other one, the null hypothesis should be either greater or equal to 46%, but 46% would be the P equal 46% would be better. So that's basically how we set up null and alternate hypothesis. So in the real world, usually when we try to test, it's based on the need of the circumstances, right? So we look into that. In this case, it's a concern about whether or not there's a bias in the hiring process. So then when P equal 46%, meaning there's no bias. When P less than 46%, then there's a bias. So there's step number one, step number two, in the calculator test statistics. And so using the z-score here, the P hat, compare the sample proportion, population proportion, and then square root of PQ over sample size. So we can look up the formula very quickly in the formula sheet. Then we are using this formula here, this one. Proportion, one population. So I'm using the z-score formula. So this turned out to be square root PQ times Q over sample size. P hat is a sample proportion. So we look into the sample, the random sample of 72 recent hires, and that means sample size is 72. And so the P hat for this sample, percentage of female applicant being hired is 27 over 72. And that will give us, let's see what that is, 27 over 72. Put into a calculator. That turned out to be 0.375. So meaning there are 37.5% of the female applicant being hired into the position. And then the P, right? P is given here. So P is this. So P is 46%, P is 1.46. And Q, right? Percentage of the male employees hired into position is going to be 1 minus P, 25. And we know all those numbers, and just plug into the z-score formula. So it's 0.375 minus 0.46 over 0.46. Over sample size, that's 72. And let's get the z-score first. Let's see what that is. It's 0.375 minus 0.46. Times 0.54 over 72. You can also try in your calculator. And that turned out to be 1.45 approximately minus 1.45. And a quick assessment is if the z-score is between -2 and 2, that's usually considered a normal range. That means this is pretty usual outcome, right? It happens all the time. Basically, we fail to reject HO. But here, they want us to use p-value method, so we also need to find out the p-value here. And based on the alternative hypothesis, we know this is left tail test. P-value is concentrated on the left tail. So using p-value method. And we draw a bell curve. Now the z-score here is -1.45. And you want to figure out area on the left tail, which is here. Based on the test of the z-score. So you go back to table A2, look for -1.45. -1.45. And the area to the left is 0.0735, right here. 0.0735. So this area here is 0.0735, and that's what we call a p-value. So p-value equal to 0.0735, and this is bigger than alpha. Alpha in this case is 0.03, meaning this event is likely, right? It's happening with a 7.35% chance, which is much bigger compared to the benchmark of 3%. So the conclusion here is fail to reject HO. So last step, fail, reject HO. So that means there's no, based on this 97% confidence, right? Based on the significance level of 0.03. So basically that's sufficient evidence to warrant a rejection of the null hypothesis that the company has been biased against the women in the hiring process. But, so if you want to put in this very technical word, it would be that's a sufficient evidence to warrant rejection of the claim that the company has been biased against women in the hiring process. Company biased against the woman. Also, in the hiring process at alpha equal at a significant level of 0.03. Use this. If you want to report it in professional, let's say in your research paper, this is the proper way to report your results. Okay. Any question about this?
I have a question, Professor.
Yeah,
Since
yeah.
the alpha
Mhm.
equal to 0.03 and is way less than 0.0735, isn't it under like inside the rejection area, the rejection region?
So that's yeah, you mentioned the other method, right? If you're doing the critical value method, actually you will look slightly different. So the critical z-score will come from the alpha, which is 0.03.
Mm-hmm.
So if you're doing that, then I'm gonna need to if you're doing a critical value method, let's see, let me get a new sheet and I'll show you if you're doing the other method, that's how you do it.
Yeah, sure.
Okay. So again, if you do the critical value method, so critical z-score,
Mm-hmm.
z alpha, it's based on this 0.03. Well, this is critical value. And so the critical z-score will come from the left tail, so z minus z alpha, minus z alpha. And the area on the left tail is 0.03. So we will go back to table A2. So this is a rejection region right here. And look for the critical z-score on the left tail. So 0.03 on the first page. Let's see. 0.03, the closest value is this one, 0.0301. And that corresponds with the minus 1.88. See? And that's what we use. So critical z-score here will be minus 1.88. So this here is minus 1.88. And look at our test statistics. See, it's minus 1.45. Double check. It's minus 1.45, right? Minus 1.45. And this is non-rejection region. This is rejection region. This is non-rejection region. Since this one is slightly bigger than this, that actually fall in the non-rejection region. So the game failed to reject itself.
Oh, okay, I understand.
So
So
same
it's quite
conclusion, right? Mhm.
So it's quite different from the last question, question 6. For this one, we have to using the critical value method to get the z
No, we
value.
are using p-value method because the question is asking specifically. We gotta use p-value method. And the critical value method, it's equivalent, right? It's equally good. The only thing is, for the t distribution, most of the time we just using the table, we have to use critical value method because there's no way to find out the p-values if you're just using the table A3, right, to look up the critical t-score. That's why.
Okay.
Yep.
So we use probability method, the p method,
Yeah, p-value method, right? Probability value method.
okay, to get a z. And from the test statistics, we got a z score and we compare whether it's falling the reject region or non-reject region.
Yeah, right, exactly. Yep. And then the critical z-score comes from alpha, right? Significant level alpha. Alpha is the area on the tail. Depends on which tail, which tail we are working with. In this case, we are
How
working with the left tail
how can we tell it's left tail or
because
two
H1
tail?
is so not equal to is two tail, and because our HO so HO we for some reason Pen is not working. Okay, so it's working. Yeah. So HO, remember first step when you set up HO P equal 46%. H1 P is less than 46%. If less than means left tilt test.
Oh, I got it.
It's greater
And the
than
last question is not equal to.
yeah,
It's
not equal
right,
to.
right
It's a
tail.
different. Yeah, exactly. That's two tail.
Okay,
If
I
it's
got
not
it.
equal to, then two tail.
Cool. Thanks for
Okay.
explaining this.
Sure. Yeah, so let's go back. Any other questions? So this question 7 and question 8. So it's about regression analysis. So you get these regression outputs and just analyzing all the results here presented in the question. So we have a table below where we're using the linear regression model to predict the price of textbook. Let's see. No, not just move this out of the space. This is good. Now let's take a look at it first, and then I'll show you the answer in about 5 minutes. Let's look at it. Let's go over this. So part A is, so we get a simple linear regression here. We are predicting the price of textbook. So predicted price, it's equal to 69.20238 plus 0.28068 times number of pages. So here the independent variable is pages. Number of pages, and then dependent variable is the predicted price. So this is our output. Then we look at the overall f-test first. Look like the p-value is very small, right? It's beating 3 star. I think, is it? Yeah, it's beating 2 star, right? 0.01. It's not beating 3 stars, but it's still pretty significant because, so for part A, because the p-value is equal to 0.00534, and it's less than alpha, right? Less than 0.01. So this f-test, overall f-test is significant. And then secondly, stated simple linear regression model. This is the simple linear regression model. Just right. And this is the model itself. And then part C, interpret B0, B1. Part C. For B0, that's $69.20. And it's when the number of pages equals 0, right? So B0 here, the interpretation could be like a fixed cost, right? Like machine, cost of machine, cost of the electricity, cost of the rent of the shop, all those. So this is the fixed cost per book. B1 is when the number of pages of the book, of the textbook go up by one of the textbook. Go up by 1 unit, by 1 page in real context. And the cost of the book, of the textbook, will go up by about 28 cents, right? 28 cents, about $0.28. Will go up by 28 cents a page. So that's how we interpret B0, B1. And D, interpret the R square. So in this case, R square is this multiple R square. So R square interpretation, so 55.5% of the variations in the price of the book variations. Price of the book. Book is 69. By the variation in the number of pages, or like by the regression model, which is this. Or you can say just by the regression model. Simple linear regression model. And then adjust the R square, in this case, adjust. It's going to be almost the same language, but it's slightly different. Right? It's 51.05% of the variation in the price of the book is explained by the regression model. All the language are the same. Take into account or take into consideration of the sample size and then number of predictor variable used. Count our sample size and number of predictor variable used. Number of predictor. That's how we interpret the adjusted R square. And for pi e, predict price of 400-page book. So pi e. I was basically just taking the number of pages equal 400. So you do predict price equal to 69.20238 plus 0.28068 times 400. That will give us the result. And that turned out to be $181.47 approximately. So the exact amount would be 181.47. $438. Which is the predicted price for a 400 pages book. Any question about this? And question 9, we're just adding additional, is the additional variable, which number of color used in the book printing. And we come up with this model here. So let's take a look at it quickly. Okay, so let's go over the solution here. So I discuss whether the predicted power of model was increased with this additional variable. So adding another variable with number of colors, and looks like it is, right? First of all, the range of the residual has been decreased. This range of residuals. There are three reasons the predicted power was increased. So the answer is yes. Number one is the range of the residuals decreases. Secondly, overall f-test slightly more significant because p-value decreased slightly. So the overall f-test slightly more significant. Third reason, it's if you look at the p-value of each predictor variables, looks like it decreases, right? We can also check that on previous question. Yeah, so pages 0.00541. Test is good. Yeah, also, if you look at the adjusted R squares, I think it's improved slightly. If you look at adjusted R squares here, it's go up. So that go up about maybe 12%. The last reason is adjusted R square. It's up about 4%. So there's a significant improvement on the overall model, right? Basically, we capture a lot more variations in the price of the textbook. So this is part A. Part B, we buy the multiple linear regression model, so the predicted price equal to 44.64962 plus 16660 times pages. Number of pages plus 17.48228 times number of color. That's overall model. And then we interpret the B1, B2. So B1 as a number of page go up by 1 unit, 1 page, and the price of book will go up by 16.66 cents a page. Taking into account holding the other variable, number of color constant. So that's the number of page. Or by 1 unit, 1 page. Or by 1. Then the price of the book price will go up by yes, 16660. Holding number of color variable constant of color used. About holding that variable constant. B2. As the number of color increased by 1 unit, as number of color go up, increased by 1 unit or by 1. So the price of the book will go up by $17.48, approximately the price of the book. Well, by $17.48. 40 the page is constant. The page is variable constant. Probably B2, and then again multiple R square, so 70 R square first. 70.16% of the variations in the price of the textbook is explained by the regression model, by the multiple linear regression model. Also, there's the R square. So that's a 63.53% of the variations. It's the same language. And just add additional piece, which was take into account of sample size and number of predictor variable used. Number of predictor variable. And so that's part D and part E. I probably need another page. So let me just put on that page. Let me share the screen. 1 second. Yep, so this one. So that's IE. A predicted price of the 400-page book with 3 colors. So here, IE. So the predicted price is equal to 44.64962 plus 16660 times 400, adding 17.48 228 times 3. That will give us the estimated price based on the model 44. You can also try in your calculator. 962 216660 times 400 plus 17.48228 multiplied by 3, and then that turned out to be $163.74 approximately. 163.373. Three, six, four, six. That's pi E and then pi F. Which model is better? Looks like second model is better. So second model, because the first R squared go up by 12%. The first R squared increased about by 12%. Second model is better. Because first R squared by about 12%. That's a significant improvement with the additional predictor variable number of colors used. So any question about this? The last one is on a logistic regression. Let me just this. So let's look at it for like a couple minutes. Now go over the solution.
Professor, I do have
Yeah.
a question
Sure,
for
sure.
question A, question 9. So I saw there is a line for the degree of freedom. On the question 8, the F statistics is 12.47 on 1 and 10 degree of freedom. And for the question 9, the F statistics decrease and the degree of freedom jump to 2 and 9. Like what I can tell from those information of degree of freedom.
Oh, so this is basically you don't have that information because we don't have the original data set. But yeah, so it looks like 1 and 10, right? If that's because it's simple linear regression, so it's slightly different from the multiple linear regression. Yeah, so that's why. And so degree of freedom dropped by 1, right? 2 and 9, right? Because because we're using two predictor variables, and then you subtract 1 from 10, you get 9. Because we add another predictor variable.
Oh,
Yeah, so that's why degree of freedom go down by 1 unit.
That makes sense.
And then the p-value actually is it's a decrease. But then that means the second model is slightly more significant.
It decrease means it's more significant.
Yeah, the test is more significant. Meaning model is slightly more significant. Statistically significant.
Oh, cool. I thought for the p-value, the larger the better. So it's the smaller the better.
No, the smaller the better. The smaller the more it's more significant.
Okay.
meaning the overall model is slightly more effective.
Okay.
Mhm. Okay, let's look at the last one, right? So researcher investigating the 2060 presidential. This is real data, right? That we did run the real data, on this. This is from the real data set. And then this is the logistic regression output from R for data set with the median household incomes in thousands, right? So the units in thousands for 20 states as predictor of the states of choice in the election. So we actually run a logistic regression, stated logistic regression model. So for pi, let's state that. So it would be ln of p over 1 minus p. The p over 1 minus p is odds ratio. So taking the logistic regression, meaning taking ln from both sides of on the left-hand side. So then, so the b0 is minus 12.456 plus 0.20602 times the income. And remember, income, the unit is thousands. And then let's look at these outputs. Look like income is pretty significant, right? If you look at the p-value for this z-test, it's beating 1 star. It's not perfect, but it's okay. Right? It's not too bad. So this is the first step, state a logistic regression model. Secondly, predict the presidential preference in the state with the income of $30,000. So here, $30,000 means 30 units. So this X value here, income, for the income, we're gonna use 30 units, not 30,000. Income is 30 units. That being said, so here, this income here becomes 30. So we're gonna get ln of p over 1 minus p. And that's gonna be minus 12.45601 plus 0.30602 times 30. And so we get ln of p over 1 minus p equal to, and let's get a single number on the left-hand side, on the right-hand side. So minus 4.45601 plus 0.20602 times 30. And this turned out to be minus 6.2754. Now we just, as we try to solve for p, but basically the predicted preference, right? Or you can say we try to figure out the odds ratio, right? And then here the Trump is coded as 0, right? Clinton was coded as 1. Yeah. So that's basically the important tool, right? So the probability of success is voting for Clinton, right? So P is voting for Clinton, 1 minus P is voting for Trump. And here predict, sure, income level. So, and then we solve for P. Okay. So here we get the P over 1 minus P equal to E2 minus 6.27541. And then we're going to solve for P. So it's going to be P equal to E minus 0.67541 times 1 minus P. And then from here, we continue, we get P equal to E minus 0.6, 6. 27541 minus P times E to minus 0.27541. And move this to the other side, we get and factor out the p, we get 1 plus e minus 6.271. On the right hand side is e minus 6.2751. And the p probability value is going to be e minus 6.2751 over 1 plus e minus 6.2751. Now we're going to find out the probability voting for Clinton. Let's see what that is. Minus 6.2751 over 1 plus minus 6.2751 and get 0.0018, right? It's very, very small, 0.0019 actually, meaning 0.0019. So at its 30K income level, only like 0.19% of chance voting for Clinton. Okay, so at it's so meaning 99.81% of the income level 30,000 will vote for Trump. That's what this means. At the 30,000 income level, only 0.19% of people, 0.19% of voters will vote for Clinton. That's basically our discovery, right, from the logistic regression model. And then the odds ratio, it's basically P. So odds ratio is P over 1 minus P. That means it's a ratio probability of voting for Clinton over probability of voting for Trump. So it's a ratio of probability of voting for Clinton and probability of voting for Trump. Not pretty on track, but voting for Trump. That's basically that's how we interpret the odds ratio here. Or we can say probability of voting for Clinton over probability of voting for Trump. I think that's probably simpler. Just say in the real context, it's probability. Of voting for Clinton first over Clinton over probability over the probability of voting for Trump. And then the last part, we need some more space. So I'm going to get another screen here. And back here, another screenshot. And basically, we are calculating the Nope, not this one. Mm. And we want to find out the income level, right? Separate the preference over Clinton and the preference over Trump. So let's see. So here, what income level yield 50% for the state voting for Clinton? So that means P equal to 50%. That means 1 minus P is also 50%. So equal chance for both candidates. That's what this means. And so ln of, so copy here, ln of P over 1 minus P, it's going to be 1, right? So ln of 1 on the left, minus 12 point, and I will try to solve for the income level, 456, 1, plus, and 20602 times income. And here on the left-hand side is ln of 1. And that's 0. So minus 4.5601 plus 0.20603 times income level. And then this is 0 equal to minus 12.45601 plus 20602 times income. So the income is going to be equal to 12.45601 over and 20602. That looks like it's around 60K, right? If income above 60K, their preference would be Clinton. But if it's income below 60K, around 60K, we get an exact number 45611 and 20602. It turned out to be 60.46. But this is 60.46 thousands because the unit is thousands. So that means it's 60,000. This is how much is the income level separated two groups, units. And translating into the income level will be $60,460 and then around 20 cents, right? But we're just going to keep it as a whole dollar, no problem, approximately equal to this. And as the income level above that, above this, prefer Clinton. Below this, prefer Trump. All right. Any question about this? Again, so we've just finished reviewing this. I will produce this video. So if you guys just join afterwards, that's okay, right? Don't worry too much. I will produce this video. I will post it in our Brightspace course, and then you can use it. I also have a handwritten like solutions. I will also post it, in a bit. But again, I hurt my back. If you didn't get my email, I hurt my back on Monday during one workout section, and I sent out an email last night around 8 p.m. I went to doctor. Doctor told me not to stay home for another couple of days before I can fully recover. So I have to stay home today. That's why. And also, there's email migration happening like in the past couple of weeks. So we are transferred to the new, I guess new email login account. It's right now it's going to be your username at login.cuny.edu, and then using the same password, you can log into the new email system. That's the reason maybe some of you guys didn't get my email. I also sent out email this morning just in case. And then during when we started the section, I realized some of you guys didn't show up, so I have to dig into I went to the CUNY first and I dig out your emails one by one, and I sent you another reminder email. That's how I know, and I asked her email me about, waiting outside of the 309. So I realized some of you guys didn't get my email. So, but again, don't worry about it, right? I will post this recording, and also I can send you the